more of an, I'll give more of explanation. Okay. I hope it's okay.
Yes, sir.
So pumping, you can have optical or electrical. What do we mean by that? Essentially, we are trying to make the carriers go into the higher excited state, right? So let's say the carriers were in the ground state, and then we are exciting into the upper state. So this is called pumping. I mean, optically, it is fairly straightforward. You take a piece of semiconductor, you pump, right? What do you have to do? The h nu of the pump should be greater than Eg if you're taking a semiconductor, right? This is the standard thing that we use. But how do we pump electrically, Kushagra?
So by
by doing what? Hello? Hello? Am I audible?
Yes, sir.
Okay. So maybe I think he has some issue. Okay. All right. So basically what happens is in electrical pumping, we can't shine a photon, right? So what we do is we build a heterostructure of, let's say narrow bandgap material between a wider bandgap material like this.
So he wrote in the chat box, PN junction.
Okay. PN junction, right? Okay. Yeah, please. Somebody, I'm not seeing the chat box. So please, read out to me if any message is there, interrupt me. Okay. No problem.
Yes.
So you have basically, this is a narrow bandgap material. And this is a wider bandgap material, wide bandgap. So I should say, instead of like this, I'll put it on the top. So these two sections are wide bandgap. So when you have such a structure, and if I dope it, I can have basically, let's say in one of the sides, I can have, let's say here, my electrons getting injected, and then I can have a holes getting injected in this fashion. So a simple PN junction will not be sufficient. The reason is, if you take a simple PN junction, what happens? You will have a situation where if you have a simple silicon PN junction, PN, there is a depletion region, you can inject, but then immediately the depletion region width will reduce. Okay. So a simple PN junction won't work. We need a more efficient form of injecting is actually to make a heterostructure like this. Okay. This is actually called as double heterostructure. All the lasers and all are made usually with this double heterostructure. Okay. The reason we call it double heterostructure is, one is, typically this is gallium arsenide, right? And this can be aluminum gallium arsenide. Is it aluminum? So basically we change the composition. Okay. So with a slightly different material, so heterojunction, not a homojunction. Homojunction with silicon. That's a homojunction. But heterojunction is basically dissimilar materials we are combining, and you're having this. So basically you have now electrons on the top here, electrons, and then you have holes in the bottom, and then they recombine and produce a photon. Now, coming to this question, why does industry want electrically injected carriers? The simple reason is, let's say if you make a chip, just think of this scenario. Let's say I have a chip like this. I want to actually use it for transmitting information on chip because I can make it more compact, right? So now if I want to have multiple lasers like this, and I want all of them to emit some photons into a waveguide. Okay, this one laser and laser 2 and so on. Now, if you have optically injected lasers, first of all, optical pumping is, always larger. You can't focus light down below a diffraction limit, right? So the area that you cover is large. And the second thing is you can't independently address various lasers. For example, right now, if you think of the, let's say the communication systems that we are using, right, for the internet. So you have the optical fibers, but there are also lasers which are actually modulated to transmit information. Okay. So you'll have something like this, wherein you have a multiple lasers, and then you'll have a common waveguide, which is transmitting information. You want to send all the information through that. Since photons don't interfere with each other, you can actually send the same waveguide, and through that we can send a lot of information. So if you want that sort of direct addressability, okay, optical pumping is not very good. Okay, that's one reason. So I'll put this to the bottom. Okay. So benefits of electrical pumping. Is rather, number one, allows multiplexing, I would say. By which I mean, I can address different lasers individually and I can combine all of that and then set it. All right. This is something very, very important. Nowadays we talked about, I think, we understand semiconductors, right? So now we have come to a point where the semiconductor devices are at the limit, right? The scaling limits. So now the emphasis is increasingly on what we call as co-packaged optics, wherein you have multiple chiplets and then you want to try to integrate them using an optical interconnect. We talked about it initially in the intro also. So if you want such a system, you want to multiplex wavelets, you can send the same, using the same channel, you can send multiple, using the same waveguide, you can send multiple channels. There won't be any interference, there won't be any crosstalk. If it's an optical wave, electrical wire, you can't send multiple signals. You can't even imagine doing that. But in case of optical signals, we can actually have multiple channels, and we call them in the industry nowadays in the optical fibers, they call it dense wavelength division.
Yeah, it's done, started.
Sorry, Balaji, I think it's not for me, right?
Oh, sorry, sir.
No problem, no problem. No issues. Thank you. So you can have dense wavelength division multiplexing. So this sort of a structure, electrically modulated structures, allows you to integrate many, many devices. In fact, in WDM right now, we have up to like 90 channels, 92 channels or so, or even more. I'm not certain what's the latest number, but plenty of channels integrated on the same fiber. All right. And the spacing between them, for example, if you're interested, 1550 is a common wavelength, we say, but each channel will be separated by, 0.1 nanometer channel spacing. So we can actually send a lot of information. For that purpose, we will require electrically injected lasers. Okay. Anything else? Any other advantage? I would say that another advantage could be, you are, for example, you want to pump the gain region. We don't need to pump everywhere, right? Let's say if you take, I would say one more advantage would be selective pumping only in active region. By which I mean, for example, in the top case here, you can selectively introduce electron hole pairs only here. You won't do anything here, correct? But if you have a optically pumped device, even where you don't have any, structures, you will pump it and there's something, either the photons will get absorbed or transmitted, somehow they'll get lost. Okay, you're losing a lot of photons to simply, unnecessarily pump is getting wasted. And that is actually thermalizing, and then it's actually heating the device. Whereas in this case, you will try to have more quantum efficiency in such a way that you inject, let's say, n carriers, n electron hole pairs, then you'll have n photons. I mean, you want to have that. So you can get better quantum efficiencies here, I think. Unless, only from certain region of space. That's what I mean when I say quantum efficient, not the total one. Okay. Does it make sense?
Yes, sir.
Yeah. So for these reasons, we would prefer electrical pumping. Okay. And now optical pumping is, easier to achieve. Okay. So advantages, basically it is harder. Electrical pumping is hard. Why is it hard? Can you guess?
So because there is sort of non-uniform
I'll tell you one simple thing that you have studied in semiconductors. The wires are going to be metal and semiconductor. What happens if you have metal semiconductor junction? Right? You have to make sure that you don't have a Schottky barrier. That is one problem. Correct?
Yes.
And then make wires of low resistance. Okay. You might say it's very easy. I'll simply put a metal like, gold or something like that, and I can easily make metal wires. But the issue is, remember here, this is semiconductor. If this density is very large, sorry, if its resistivity is very large, then there'll be some voltage drop across this, and effectively the overall resistance will increase. So that's why, let me try to go back. This is in week 6, 7. I forgot. This is metasurfaces. So maybe in week 7, maybe. Yes. So if you look at some of these nano lasers, you see here, this one. We said that this is your bottom contact, right? Here it is connecting. So you have some very high doping here and here as well, right? This is 10 power 19 doping is almost like degenerate, I mean, very high doping. Here also high doping, and you try to make as high doping as possible, because if you have large doping here, low doping here, the resistance will be large. Similarly, on the top also, you will have high d-doped regions here. Okay. So if you have high doping, again, there are some other things that are an issue. All right. It's in gas, sorry, not, we'll have to, yeah. Okay. So this sort of, we'll have to verify, gas and L-gas or in gas, what will work? Indium phosphide, indium arsenide has lower band gap, I
Lower
think.
band gap. Yes, sir.
Yeah, aluminum gallium arsenide will be fine.
Yeah, yes, sir. This is correct.
This is correct. Okay, fine. Yeah.
Yeah.
So yeah, we just have to look at the stoichiometry here carefully. All right. So this is my answer. Any other questions, Kushagram?
Yes, sir.
Yes,
Sir,
tell me.
for a single nano laser, if current would be in microamperes or milliamperes, that won't be too much for a single nano laser.
Yes, ideally we would like to reduce that. That is true. Okay. I think still we are not, I mean, if you look at, I told you about, I think in the introductory part, right? I told you about how much energy is getting consumed per bit, switching a bit, right? This is in week 7, I think, introductory part, I talked about it. Yes, why we need to miniaturize, right? So right now the thresholds are high. If the threshold is high, we have to actually inject more and more carriers to actually overcome that threshold. Okay, that is why the threshold is high. So finally, if you look at nano lasers or any lasers, right, we will actually refer to what is known as a Li curve. Okay.
Yes, sir.
So I have basically I versus L curve. There will be some sort of an increase. There will be a threshold and then current increases. Okay. I threshold. If the threshold itself is high, then I'll have to go even higher to get a lot of light. Okay. So ideally, yeah, this will have, I mean, we want to have lower thresholds. That's one of the goals, right? We want to reduce it. Okay. And we also want to reduce the size, because if you right now, do you agree that the threshold depends on the area of the device?
Yes, sir.
So if you have larger area, then loss is more. So that's why that threshold will be high. So if you miniaturize, hopefully we can reduce the thresholds as well. Correct? So that's the goal. That's one of the other driving factors for actually getting nano lasers.
Sir, instead of making contacts of metal, can we use some transparent oxides, so that can reduce some heat losses? So threshold.
Okay, let's compare. Okay, the question was, can contacts be transparent oxides? Okay, transparent conducting oxides, TCOs we call them. Okay, yes, instead of metals. Now the issue is, think about it, which will have more losses? Okay, losses.
So metal would reflect. I mean, if we optically pump a metal would reflect the photons, then threshold would be high by.
Okay, yeah, optically pumping metals will be a problem. So you want TCOs, correct? For example, solar cells, we try to put TCO as a contact. Okay, because if you put a metal there, no, it will not get through, and then you can't get any light inside the P junction. Correct? So TCOs are necessary there. But for lasers, we want actually to pass a lot of current. Correct? So losses depend on depends on I square R, right? This is Joule losses. Okay. So now current is whatever I need. If I have my threshold, I have to supply that much of current. But what about the R? R of TCO versus R of metal. Which will be better? Yeah. TCO has larger resistivity. Right?
Yes, sir.
Larger resistivity. So for lasers, if you have ice, it will actually start heating the device if you don't have metals. That way, they are not an ideal candidate. But you might ask, okay, fine, you're putting a metal and you're trying to get light outside. Sorry, you're able to how if you have this much of metal, how do you get the light outside? Correct?
Yes.
Where is the light getting generated? It is only getting generated from the active region here, right? How is the light coming out now then if you put metal? Well, that's why you have to optimize how much is the thickness of the metal and so on. Metals also can be transparent if they are thin. If you make it very thin, then the resistivity increases. Okay. So an optimization game. Okay. Metal contacts need to be thin for extracting light. But very thin metals have higher resistance. So basically, optimize for both. Optimize thickness of metal. Right? And this, even the short key contact, everything will come into picture. You have to optimize everything. Okay?
Yes, sir.
Anything else?
Yes, sir. One more question. So,
Sure.
You were, sir, describing the fluorescence versus the pump pulse area graph. So my doubt was, sir, why it's happening at 2 pi pulse area, the fluorescence is less.
Yes.
Why are we seeing the uptrend when the pulse area is 3 pi? What I was thinking that for 3 pi pulse area, intensity would be less. So the cross section of suppose any molecule that it will excite the photons to the excited state will be less. So the fluorescence should be less. The quantum yield should less. So why are we seeing an uptrend at 3 pi pulse area?
Okay. So the main issue here is, this is the graph you're referring to, right?
Yes, sir.
So now let me change to different sheet altogether. Okay. So the question is, why fluorescence shows uptrend at 3 pi, in Rabi oscillation graph. Okay, this is a question. The issue is, what we are saying is, let's say you have level 1, level 2. Okay, this is level 1, I'll call it. This is my level 2. Provided there is, let's say there is n atoms here. Okay, let's say n naught atoms. Okay, initially they're in the ground state. Okay, so what we are saying is here, as you pump, what happens? Okay, as you pump, provided your Rabi frequency is much greater than the relaxation rate, what happens is you take these n electrons in the ground state and you put them in the upper state. Okay, do you get that?
Yes, sir.
So that's how we do all the pumping, right? But the issue is, if I, let's say, out of this, I'll make n1 here. Okay, I'll make n1 here, and then this will be n0 minus n1 in the ground state, correct? But at some point, if you just wait for the radiative decay, then this will start decaying also, right? That's what usually happens. But provided your Rabi frequency is greater than the relaxation rate, in this week 7, right? Week 8. Provided you meet this condition, right? Before it can actually radiative decay, you will see that the superposition of the probabilities will essentially happen in such a way. We talked about this, the population density in the higher state and the lower state, right? So it so happens that the population will go up, it will come down again, it will emit like this. Okay. So now, at let's say some time, right? Initially, initially if it is this, after some time, after when it's a pi pulse, okay? In the case of pi pulse here, See here, the population is maximum. So at pi, ideally what should happen is the population here is 0 and here it is n naught. Okay. And
Yes.
then when you apply 2 pi, what happens is it again flips. You get n naught here and then you get 0 here. At 3 pi, you get 0 here and not here. And 4 pi, you get n naught and 0. So what we are saying is this graph we showed you here, right? This is the probability. Now we didn't really go into all the details, but what we said is you will have this Rabi frequency and then you will have this oscillation of population density. So this C1 square, whatever I'm calling it, that is a dark line. So it starts out with 1. That means the highest state has, let's say lower state has, C1, right? So lower state probability is high. So all the atoms are in the lower state. Now, as you go to certain time, you will make sure that it will actually go to the higher state. Then again, if you continue pumping, it actually goes back up to the lower state. Okay, that's what I'm showing you here. Is this part okay? Is it making sense?
Yes, sir.
So now, where will the fluorescence be maximum in this picture?
At pi and 3 pi.
Exactly. So fluorescence maximum. And then these two places, fluorescence, FL minimum, I'll say. Okay. So basically, by looking at my fluorescence signal, I'm understanding whether, in this case. So initially there was nothing. If you just make the pulse width different in such a way that the overall intensity in this dimensionless units, it becomes pi, 2 pi, 3 pi and all that, you will see that the fluorescence is maximum. If you apply 2 pulse, the fluorescence becomes minimum and you're able to put fluorescence maximum and so on. Okay. But of course, after some time, it's going to decay. The Rabi oscillations will decay, right? So that's why eventually you'll come to a point where, nothing happens. But, if you engineer in such a way that your intensity is large, because Rabi oscillation frequency is dependent on the intensity. If your intensity of the pulse is large, then overall I can create a situation where I can deterministically put an atom in the higher state or the lower state. Okay.
Yes, sir.
This is a very, very interesting concept that a lot of people are now using, for very, very fancy things, For example, let's say, there are something called atom interferometers and things like that. We might have studied about Michelson interferometer or Mach-Zehnder interferometer. Two
Yes.
lights, go and then they merge and then you have interference fringes and so on. You can actually do that even with atoms. Okay. So have such a thing when I have atomic interferometers. These are, atomic physics, we call it, atomic molecular physics. So wherein we can actually detect even very, very sensitive rotations, accelerations, and so on. So we can build gyroscopes and accelerometers and so on. So now you see that there are a lot of efforts to try to, build them. Of course, these are bulky equipment, but they can be very, very sensitive. Like for example, the acceleration due to gravity, right? If you want to measure, G for Earth is 9.8 meters per second square, right?
Yes.
So now, if you want to measure it, there are some, in your phones and all, there are these gyroscopes and accelerometers which will tell you. And because of that, you're able to, calculate distances and all that. Okay. But if you want to do a very sensitive one, you can actually, with these atomic interferometers, we are able to build, or at least some proofs are there, wherein people are trying to build, accelerometers sensitive to almost 10 power minus 9 G. Very, very small changes in the acceleration due to gravity or acceleration they can detect. Okay. So this sort of things are possible. So these extremely sensitive measurements are possible. And for some things like that, in those processes, we want to deterministically put an atom either in the ground state or the excited state. Okay. And now we know how to do that. All we have to do is find in such a way that you find the intensity of these, you find out, what is the damping rate, and then find out, tune your intensity such that it's very high, and essentially create a system wherein you calculate the pulse area. That means you control the pulse width, essentially, right? You control the pulse width in such a way that you either deterministically put your thing in the high excited state or the lower state. For this purpose, all we have to do is we have to change the area, that's it. Or keep the area fixed and then change the intensity.
Yes.
Both ways you can actually control. So you keep changing the intensity because pulse area, pulse width is difficult to control. You keep changing the intensity and you keep measuring fluorescence. You automatically see this oscillation. You know what is intensity for pi and what is for 2 pi. So put that. So automatically your atom is kind of prepared to be in the excited state. Okay.
Yes, sir.
So this pi pulse, 2 pi pulse, you will see a lot in these kind of domains, some of the frontier domains in this. And if you are able to do such things, now they're trying to put them on satellites and so on. So I mean, a lot of interesting things are happening. Yeah.
Yes, sir.
Okay. That was the question. Any other question?
No, sir.
Okay. All right. Thank you.
And so, sir,
Yeah.
these dampings which we are talking for Rabi oscillation, these dampings are the intrinsic property.
Yes.
Okay.
So basically, I mean, how much? See, it will finally depend. One of the things it will depend on is the spontaneous emission rate. Once you put the atom in the excited state, it will emit back.
Yes.
Okay. After some time, it will not stay forever. Of course, for some things we need it to be in the excited state for a longer time. But again, that's a property of the material. And in solids, it's quite low picoseconds. In gases, it's slightly better. This is seconds per second, right? Sorry, yeah. This is a lower rate. So that's why some of these atomic interferometers I mentioned, right? They are done in gases. Rubidium and cesium atoms, they do. So solids, I think it's almost impossible to see it. Yeah. Okay.
Thank you, sir.
Thank you. Any other questions? Anyone else? I mean, anybody else is there or only him?
No, sir. No one is there.
No one is there. Okay. All right. So let's just read Jinal, can you read the other questions, please?
Yes. Sir, I think along the same topic, one question was why exactly we want Rabi oscillations?
Why exactly we want Rabi oscillations? Because we want to deterministically put an atom in the excited or the ground state.
The same student, he has asked, is pulse width and line width of pulse laser different? And thus line width of a pulse laser makes sense. It should be very broad.
Okay, so let's think 1 second. So is the pulse width and the line width
of pulse laser, are they different or the same thing?
Okay, that's a very nice question. So what you're asking is, let's differentiate this. What do I mean by line width? Okay. What I mean by that is, let's say if you have a perfectly monochromatic wave, what happens? Okay. I'm sorry, you're hearing some background?
Little.
I'll just close the door. Just a minute. I'm sorry. Yeah. So if you have a perfectly monochromatic wave, then essentially you have it expanding to infinity and this sort of sine wave will go on, right? If you have such a wave, you will have line width which is very, very sharp. Correct? If we say this is let's say, for example, 632 nanometers. Okay. But in effect, what we will do is, we will never have such a thing, right? We are going to truncate it. If you truncate it, what happens? In time domain, if you truncate it, it's basically this one is going to infinity. And this one is going to minus infinity. Then you have a perfect line, delta function. But the moment you apply a window like this, if you truncate it, right? Truncate the wave, right? By a window, some sort of window. Then what happens to the line width? The line width becomes broader, right? FWHM. So basically, here, this is line width becomes broad. Correct? That's what we're saying. So there is a so this is my line width. When I say line width, I'm referring to the frequency domain. Okay. This is basically a frequency domain expression. Frequency or wavelength. Okay. That's the line width. When we talk of pulse width, we're talking about this window. Okay. This is pulse width. Okay. You can say that if you have a large pulse width, I'll have lesser line width. I mean, provided nothing else is at play. Okay. Otherwise, even if you don't have, even if you have infinite wave, you still have some sort of a collisions and line width. There are homogeneous broadening mechanisms, but actually gives you slightly broader, line width. But in effect, so did I ask this? Did I answer this, Jinal? So is the pulse width and line width same? That's the thing.
Yeah, yes, sir. That was the first part of the question, and the other part was like.
Wait. No, I think his question was, is the pulse width and line width of a pulse laser different?
Oh, yes, sir.
Of pulse laser. Well, I mean, so basically the question is whether, you're at what pulse widths we are talking about, correct? If you, for example, if you build a nanosecond pulse width, okay, will that actually cause this broadening, FWHM that you see, is a question. Let's say I'm talking about 632, right? Maybe there is some amount of, maybe plus or minus 2 nanometers is a line width that I'm getting. Okay. You might actually, there is something called Fourier transform limited pulses. Fourier transform limited pulses. You will see that when you make the pulse width extremely small, then you start seeing that, okay, the line width becomes broader. Okay. If you don't, the pulse width, let's say of nanoseconds, it may not really reflect as, the real broadening in the line width. Okay. It depends on how short the pulse width is. If the pulse width is large, it doesn't really matter. If you have a millisecond pulse, it will have no effect on the line width. But the moment you go to hundreds of picosecond or even 10 picoseconds or something like that, then I think, we'll have to actually compute and see what is a Fourier transform. I don't really work in this domain on a regular basis, so I don't have it on the tip of my hands. But I think that's one of the issues. All right. So we'll have to think about, if it's extremely small pulse width, of course, then it matters. Otherwise, it does not. Did I answer your question?
Yes, sir.
Oh, okay. This guy is not there, right? And anything else?
Sir, I think you answered then the second part. The second part of the question was, does line width of a pulsed laser make sense? No, as you mentioned, it depends on what is the duration of the pulse.
Right. Okay. Does line width of a pulse laser make sense? Huh? Yeah. It makes sense. Of course, it's important. Yeah. It depends on how much you're. Yeah. Correct. Okay. What else? The line width should be very broad.
It's telling to be, but. Sir, like I have a query is like this line width is regarding the the monochromaticity of your laser source.
Right.
But the pulse width is like we have two modes of operation, CW and pulse to laser one.
Correct.
So like why should it matter that much? Like because of the source, because we always say this frequency is determined by the source.
Right.
And this modulation or all these pulse laser operations, we do it like kind of post processing. Like once the light is emitted, then we have other optics and all that to make it in the pulsed operation mode.
Well, not always, right? For example, in a diode laser, I can just pulse my current.
Yes, sir.
So,
yes.
in that case, what is the line width of pulse laser? If I'm pulsing my current, what's the line width? We'll have to check basically. Generally what happens is we assume this is we assume it's a Gaussian pulse or something like that. And what is the kind of widths you're getting? You will never really get this sort of a perfect, thing.
Yes, sir.
So there's a lot of, especially in the femtosecond domain, there's a lot of work that is done in trying to understand whether it's a Fourier transform limited pulse or not, and so on. And then there are a lot of advantages and a lot of things that are there. Yeah.
Yes, sir. Yes.
So I hope, yeah. So, what were you trying to get at? I stopped you unnecessarily in between.
No, sir, the same thing. Yeah, I was. Yeah, but now when you said like, then I understood. Yeah, you're in some way you're modulating the source also, so it will have an impact on the line width. Like
yes.
Yes.
Yeah.
Yes.
So yeah. So basically, we have to compute. We have to compute a Fourier transform and check. Assume a Gaussian pulse. Okay. Assume the line width also is Gaussian. You will start seeing that by just simple Fourier transform. You can actually do it in MATLAB or Python or something. Simply assume your frequency domain pulse to be Gaussian. Compute a Fourier transform and see what is a time domain thing. you increase the width and you will see the decrease. It's a standard, it's a simple thing. You can do it in a few. I mean, perhaps here we can actually put an assignment on this. Okay, let's see.
Yes, sir.
Okay, anything else?
No, sir, that question is done.
Okay.
Kushagra himself asked all these questions. One student asked why is it difficult to make terahertz based nanomaterials, wires, etc.
Why is it difficult to make terahertz nanomaterials and wires? Huh?
Mm.
Well, I think he's talking about the terahertz metamaterials, where I talk about the scaling of metamaterials, I think. Okay, so I think we were talking about all this, no? I think at some point I started talking about terahertz. Yes, I said we started moving from visible, yeah, here. This is probably where he was. So we started making this, and then now if you come to terahertz, and then in hundreds of terahertz, it's becoming harder. So what was the question? Why is
it difficult to make terahertz based nanomaterials and why?
Yes. No, the reason is, first of all, there are multifold reasons. Okay, he said nanomaterials, huh?
Yes, sir.
Metamaterials. I guess he means metamaterials.
Yeah.
The reason it is difficult is lithography. Okay. For example, okay, I'm just trying to convey my point. If I ask you to draw a line which is 1 centimeter, one box, let's say rectangle, 1 centimeter by 10 centimeters. Okay, you can easily draw it. You can take a scale and then draw a rectangle. I mean, of course, let me do this. I can easily draw a box of this fashion, right? A nice rectangle, 1 centimeter by 10 centimeters, let's say. But if I ask you to draw a rectangle which is tiny like this, let's say, do you find it hard or not? This is, let's say, I don't know, 2 millimeters, 5 millimeters by 50 millimeters, maybe something like that. It becomes harder. Once you actually go down to smaller, decreasing dimensions. So basically, if you decrease dimensions, lithography is challenging. Okay. So if you look at the week 8 of the course, we talked about the fabrication, right? In the fabrication, we told them that, I think we did a little bit of fabrication. Yeah. So PCB was fairly straightforward, but we talked about all these different types of approaches, right, to fabricate. Now you see that once you try to make them smaller, these techniques don't work. And then we have to do a lot of correction.
Yes, sir. Actually,
Hello, Balaji.
Yeah, please go.
I'll anyway wrap up in 5 minutes. Okay.
Yeah, it's
I think
already
most of the
streaming, sir. It's
Huh?
streaming
Sorry?
only. It's already streaming, sir. You can.
Okay, sure. I can do that. Yeah. So we'll just continue this. So I was talking about the sizes, right? The sizes were basically, if you try to make it smaller, the lithography becomes challenging. Okay. Actually, in fact, not only lithography, all the nano-fabrication processes become challenging. Okay. So nano-fabrication is challenging. So one thing you should agree, for example, in the case of split ring resonators, right? We showed you these dimensions. I think in this case, I've shown you various dimensions. In the case of gigahertz, these dimensions are in millimeter scale. It's relatively large. So it's easier to, but then the moment you come to terahertz and even hundreds of terahertz, the dimensions of the split ring resonator scale inversely, right, with frequency. So if you take a split ring resonator, for example, here, like this, the dimensions scale inversely with operating frequency. Okay. So if I call this as, let's say, A, right? A, for what we are doing is initially gigahertz. If 10 gigahertz was RF. And then 1 terahertz is roughly IR. 100 terahertz is roughly visible. So if I try to go higher in frequency, frequency increases, the size increases in the opposite fashion. Size increases in opposite fashion. Okay, and that is why if you want to go to higher frequencies, we need to make sure that the dimensions are small, and when you try to make smaller dimensions, it's harder. Okay, that's the issue. All right. So yes, I hope that was. Is anybody there now here? Let's say Jinal.
Yes, sir. Yes, sir. This was.
So that was the question, right? Anything else?
No, sir. Like,
Okay.
there are no other questions left.
There are no other questions, no? All right.
Mm.
So, all right. Anyway, thank you, everyone. Thank you, Kushagra, for joining back as well. So, we'll, yeah. Any questions you have?
No, sir.
So, I mean, I think we didn't do initially some sessions. So, but initial part of the course, right? There were a lot of new concepts. Is it okay? At least it makes sense. And how are the assignments and so on?
So assignments are good. Some questions are tricky. We need to visit the lectures again to solve them.
Okay. Okay. We'll see. Yeah. We'll try to make them simpler. We'll see. Okay. Good. All right. Yeah. Thank you. Thank you very much. And I'll try to host one more session in both courses, the semiconductor course and this one also. I'll try to do it early next week again. Okay. Let's interact more. Now I'll get a little bit free in the next week. So we will try to interact more. All right.
Yes, sir. Thank you.
Thank you very much. Yeah. So we can stop the session now. Is Balaji there? No? Or Balaji, can you hear me?
Yes, sir. Yes, sir. I will close the now. Thank you.
Close.